Hey, welcome back. It's a new section here. It's a brand new morning, at least for me recording this, and most importantly, a brand new data structure, the graph. So I love graphs personally. They're fun to teach, they're fun to implement, but most importantly, they're really, really useful in today's world. Graphs are used in basically any social network. Anytime we're modeling users and recommendation engines, for example, when Netflix recommends another movie or something to you, or advertisers target you based off of something, graphs are usually in play. And when I say graph, we're not talking about a chart, which in English, often we also call a graph. I'm not talking about this sort of two-dimensional looking chart. It's a data structure. It's very different than this. So what it is, we'll get to in just a moment, but first, our objectives. So explain what a graph is. Obviously, got to start there. Compare and contrast different types of graphs, and also we'll compare and contrast graphs to other structures we've seen, like trees, which, hint, hint, are actually a sort of a special type of a graph. And then also talk about their utility, their applications in the real world. Then we'll implement a graph using something called an adjacency list. So there are multiple ways to implement graphs. I'm just going to show you one, the adjacency list, and we'll talk about why. Then we'll traverse through a graph using our good old BFS and DFS, breadth first and depth first search. Compare and contrast graph traversal algorithms. We'll talk about Big O along the way, talk about some fun algorithms. But let's get started by just talking about what a graph is. Take it away, Wikipedia. A graph data structure consists of a finite and possibly mutable set of vertices or nodes or points together with a set of unordered pairs of these vertices for an undirected graph or a set of ordered pairs for a directed graph. Okay, did you get that? Yeah, that doesn't really make much sense, or probably doesn't make a lot of sense. It's kind of clunky. Really what it comes down to is a graph is a collection of nodes and connections between those nodes. So if we go back and read that definition again, let's just sort of skim through it. A finite set of vertices or nodes. So let's just say a set of nodes together with a set of pairs of these vertices. So those are the connections. So we have a bunch of dots, a bunch of nodes, and then connections between them. So this is a valid graph. These are the nodes and these are the connections. Here's another valid graph. The same nodes, just different connections. So the placement of them in this diagram doesn't matter. We could have this same structure. It's just the connections that are important. But if this B was way over here or this F was way over here, it doesn't matter as long as we have the same lines going, the same connections. It's really just about those lines. Okay, so this is a valid graph. Here's another one. We have some nodes with connections between them. Do I have one more? Here we go. A very different looking one. The same number of nodes, the same letters for each one, but different connections, different lines. So if we go back to something like a linked list, when we talked about linked lists, we had nodes that are connected in a linear fashion. When we had, trees, we had nodes that there was one parent, one topmost node, and then from there were a bunch of children that descended from that one node, and each parent could have its own children and so on. So a tree is a type of a graph, but in these graphs that we're looking at here, there is no parent node, there is no starting place, there is no, entry point. These are all just nodes. They're treated equally, and they're connected in different ways, and those connections can mean different things. Let's actually talk about a few examples, first of all, of where you would use this.